Hello everybody, my name's Joanna Caudle and I am a mechanical engineer turned teacher. I spent about half my career as a mechanical engineer working for a big global construction company, and then after about 20 years now, I transitioned to teaching, and I've been teaching physics and an engineering elective and also coordinating a STEM program at a high school near DC. I'm so excited today to welcome you to this challenge. I think it's such an interesting topic, machine learning. And I thought I'd start by telling a little bit about myself and my journey to engineering, and then we'll dive into the challenge. So I wanted to share a bit about my educational background. I did a program that is a little unique, I think. It's called a dual degree program. And the benefit of it is it allows you, number one, to not have everything totally figured out before you go to college. Believe me, you don't have to have everything figured out in high school. And secondly, it allows you to explore a few different majors and degree programs before ultimately deciding. And then in 5 years, you come away with 2 degrees. So for me, this was particularly a valuable program for me to be involved in because I was an international student. I'm originally from England, and my parents were from England. We didn't know a whole lot about the American college system. And so for me, it was really helpful to have a bit of time to explore some majors and also to get my feet under me as I was heading off to college from high school. So I did a program starting at a small liberal arts school called the University of the South. It's located right outside Chattanooga in the mountains. And there I studied physics, math, courses that I'd enjoyed in high school, but also English, geology, art history. It allowed me to have a bit more time to explore some different subjects and learn what I really was passionate about. And what I discovered was I really liked the applied aspects of math in physics. I really liked how you could use math to model the physical world. And then, of course, the cool things that you get to study in physics. But because I liked the hands-on aspect of my science classes so much, I thought that engineering would be a great option for me. And so I did choose to do this dual degree program. So after 3 years at Sewanee and getting all my prerequisites out of the way, I transferred to Georgia Tech in Atlanta. And there I began to study mechanical engineering. I chose mechanical engineering because I found that I was really enjoying classes in physics like thermodynamics and fluid mechanics, the classes that allow you to look at the flow of heat and energy through systems, the flow of fluids and air across surfaces. And so I thought I could get into airplane design or engine performance design as I went off to engineering school. I continued to take those classes and learned about studying the performance of cycles and system to try to optimize, get as much out of a cycle, as much energy out of a cycle as possible, so to optimize the performance. And that kind of study really lends itself well to the power sector. So when I graduated from school, from college, I went to work as a mechanical engineer for a big global construction company called Bechtel. I should say that with this dual degree program, another nice thing is you get to graduate with your peers from your first college after 4 years. And then you go back and finish one more year at your second school, at your engineering school, and then you graduate with your fellow students from your engineering school. So you still get to sort of be in both colleges together. You don't have to leave all your college friends behind from one school when you go to the next one. So think about that as an option. There's currently great options where you can go to community college and get your prerequisites out of the way and then transfer to engineering school. There's technical schools that allow you to do these kinds of dual degree programs. So it can be a great way to give you a bit more flexibility if you don't quite have it all figured out yet. So what did I do as a mechanical engineer in the power business? I was responsible for the mechanical systems, the mechanical design on a power plant. Those are things like the pumps, the heat exchangers, the turbines that produce the electricity. And so the picture in the top left is a boiler feed pump. This is one of the major pumps in a power plant cycle. And it's responsible for taking water from a reservoir and pumping it to a boiler where the boiler heats it up, turns it into steam, and then it moves on to drive a steam turbine to produce electricity. These pumps are very, very large, thousands of horsepower, and if you were to stand next to one, you would probably only come up halfway in that impeller, that creamy impeller section that you see in the picture. As a mechanical engineer, I would have to understand the performance needs for this pump, and then I would write a specification and send it off to vendors so that they knew they needed to see if their particular kind of pump could produce the performance I needed. They would offer me a proposal and a price, and then I would evaluate those proposals that different vendors provided and make sure they met the design requirements and do a cost analysis and ultimately choose a supplier to provide the pump. I would also do this for things like heat exchangers or big tanks that we needed to install on the site. So mechanical engineers were responsible for some of that mechanical equipment and the design of those aspects of the plant. But we always worked in a concert with a group of engineers, civil engineers, electrical engineers, control system engineers, engineers, construction personnel, startup and testing personnel, a very diverse group of backgrounds and people that you're always working together so that when you're building something so complex as a power plant, you always have this team that you're working with. And that's something that I love about engineering, this collaborative approach to things. Also, the ability to meet and work with experts in different areas. I got to work with specialists in noise abatement when we were building power plants in sensitive areas. I got to work with specialists in environmental protection to make sure that we weren't harming the surroundings when we were building a plant. I worked with community representatives to make sure that we were understanding the needs of the community. So it's an incredibly collaborative job and so exciting when you're building something so complex like a power plant or a new car or who knows what. So many, use your imagination, airplanes, rockets. The final picture is a special one for me because it's the last power plant that I got to build before transitioning to my teaching career. I got to see this plant, which is a combined cycle natural gas-fired plant in Sacramento, and I got to see it go from just an idea on a piece of paper to a preliminary design, and then detailed design, construction. I went to oversee the performance testing and startup, and ultimately got to see it go into commission and was there for the celebratory commissioning party. So for me, these are some of the best things about engineering, is seeing something go from just an idea on a piece of paper to something real and tangible that helps a community and provides a service to a community, and also to be able to work with a team of amazing people to solve really hard problems. So let's get to it. Let's figure out what machine learning is all about. I was really fortunate to work with 2 engineering students from Notre Dame on this challenge. James and Gigi were so great and provided so many creative ideas that helped support the building of this challenge. And so I hope that as you work through this in the next few classes with your classmates, that you find things that speak to you in particular. Hopefully you'll find something that is really interesting or something you want to pursue or look at in more depth. Have you ever wondered how apps like Siri or the machines like Alexa learned from their users? How is it that that music streaming service you use seems to know what great songs or artists to recommend to you? The answer is data. Millions and millions of pieces of data. With the increase in processing speed and memory, today's computers can be programmed to take in lots and lots of data to try to find patterns that can then be used to predict the next step in a process or provide an answer to a question. And that process is called machine learning. Machine learning is one area of artificial intelligence that is concerned with the idea of replicating human intuition in computers. That sounds like pretty big stuff, but I promise we're going to break it down and hopefully make it more understandable for you. So let's look at some basics. Let's start with some background information. What is machine learning? You may not realize it, but machine learning drives many processes that you use every day. This little video that I'm going to show you will help you learn a little bit more about how a computer machine learning algorithm is a little different than a normal computer algorithm. And it's going to use the case study of the classic game of rock, paper, scissors.
So let's start with a very simple example. Consider you're creating a game of rock, paper, scissors. When you play this with a human, it's very basic. Every child can learn it in just a few minutes. Now let's take a look at the most basic part of a game that the human brain is really good at, and that's recognizing what it's actually looking at. So consider these images. Most people can look at them and instantly recognize which ones are rock, which ones are paper, and which ones are scissors. But how would you program a computer to recognize them? Think about all of the diversity of hand type, skin color, and even people who do scissors like me with their thumb sticking out, and people who do scissors with their thumb in. If you've ever written any kind of code, you'll instantly realize that this is a really, really difficult task. It might take you thousands or tens of thousands of lines of code, and that's just to play rock, paper, or scissors. So what if there was a different way to teach a computer to recognize what it sees? What if you could have a computer learn in the same way that a human does? That's the core of machine learning and the path to artificial intelligence. So traditional programming looks like this. You have data, for example, a feed from the webcam, and you have rules that act on this data. These rules are expressed in a programming language and are the bulk of any code that you write. Ultimately, these rules will act on the data and give you an answer. Maybe it sees a rock, maybe it sees a paper, and maybe it sees scissors. But what if you turn this diagram around, and instead of you as the programmer figuring out the rules, you instead give it answers with the data and have the computer figure out what the rules are? That's machine learning. So now I can have lots of pictures of rocks and tell a computer that this is what a rock looks like, and this is what paper looks like, and this is what scissors looks like. And I can have a computer figure out the patterns that match them to each other. Then my computer will have learned to recognize a rock, paper, and scissors. That's the core of building something that uses machine learning. You get a set of data that has patterns inherent in it, and you have a computer learn what those patterns are.
So how do computers do this? How do they take in this enormous amount of data in order to recognize words and numbers and images? The answer is machine learning algorithms. There are many models that researchers and data scientists have created over the years. And some of these models are really well suited for image data, others for sequences such as text or music, some for numerical data, and others for text data. Could you think of some other examples where machine learning programs might be very useful tools to detect patterns in data and make decisions about them? You may have thought of applications like email spam filters or credit card fraud detection, or perhaps advertising programs that send you what sometimes seems to be super specific targeted ads. Machine learning is also being used to analyze millions of medical images to better detect tumors in human tissues. So there are many, many, many applications for this type of technology. This slide is another way of looking at how computers make decisions. An algorithm can be any set of rules that is used to solve a problem. But we often think of this as how computers solve problems. The way a machine learning program or algorithm is different is that you give a computer a teaching set of data from which it identifies patterns, and you allow it to analyze a new set of data and make predictions. The more data the computer analyzes, the better it gets at its predictions. It gains experience and refines that model it's using to get more accurate decisions. So I'm now going to show you an example of a machine learning algorithm that tries to predict the numerical digit from a handwritten digit on the left side box. Okay, so this is a digit recognition algorithm, and you can see that it's using something called a convolutional neural network. That's a big word, and I'll explain it in a few minutes, but let me just demonstrate how it works. I'm going to write a digit on the left and try the number 9 and see if it recognizes it. It didn't quite get it, and you can see that it had a half. It's predicted that it could be a 1 or it could be a 9, and it chose a 1. So it made a prediction based on a model that it's using. Let me see if I can draw the 9 differently and see if it makes the prediction better. Okay, this time it really thinks it's a 7 and maybe a 3. You can see from the probabilities. But maybe you're starting to get an idea of what this computer algorithm is doing. Let me try it again. Maybe I can get it better this time. There we go. This time it really knew it was a 9. So how does it make those predictions? How does it think about the number that's being written on the left? What is the computer seeing? Let's take a look. In this slide, you can see on the left side is a sample of a famous set of handwritten digits. It's called the MNIST database of handwritten digits. On the right side is a blown up image of one of the digits, the number 9. And as you can see, this image is made up of a 20 by 20 array of pixels of varying scales of brightness, varying gray scale. This is how a computer sees this image, as a series of 400 pixels, in each pixel a number representing the brightness. What does that look like? It looks like this. This is a lot of data, but basically that's that 20 by 20 array, and in each of those boxes is a different level of brightness. Now, right now, I know it's very hard for you to see that that's a 9, but if I show you the pixels with the brightest grayscale, with the brightest levels, you can see the image of a 9 start to emerge. And this is how a computer sees the number 9. The type of algorithm, as we mentioned, that would be used for this kind of learning is called a neural network, a convolutional neural network. This is an algorithm which can take an input image, assign an importance, like a learnable type of weight, in this case perhaps the grayscale value, to various objects in the image, and then be able to differentiate one from the other. So here on the left are an example of all the handwritten 9s. You can see them all circled there. And that was what the computer used to learn what the number 9 is. You can see that there's models for all the digits 0 through 8 as well. And what the computer does is it looks at the 20 by 20 array of brightness levels, and it tries to choose the correct model. Is it a 9? Is it an 8? Is it a 1? And then it assigns a probability to that. So that's exactly what we saw in the program example that I showed you. I recognize that this is pretty complicated stuff, but don't worry, you're not going to be developing a neural network to recognize digits today. We have a simpler challenge that we hope represents the steps that a computer uses to do a machine learning algorithm. Before we get started on the challenge, I'm wondering if any of you are thinking, are there things a computer can do that we humans can't? And conversely, can you think of things that humans can do that computers can't do? You may have thought about data again. Computers are able to look at millions and millions of pieces of data very quickly compared to humans. A computer can scan the pitch and tone of millions of songs very quickly to suggest another song for you that you may want to add to your playlist. But humans are really good at just taking a few examples of something new and starting to learn to build a model or to make a decision about it. Computers would need much, much, much more data in order to do that as well. But this doesn't even consider things like having good judgment or being able to understand the situation to make a wise decision. So, with all of this background, let's get to the lab activity today. Here's what you're going to do. You are going to build a catapult. You're going to use the catapult as your machine, and you're going to learn how it performs by varying several input factors. And then you're going to use the data that you collect to create a model that will then try to predict the distance a projectile will go when you launch it. Now you might be wondering, we've just been talking about machine learning. Why are you asking me to build a catapult? What does this have to do with machine learning? Well, we wanted you to see that we're asking you to build a catapult to learn about the performance characteristics of a machine. We know that machine learning is a really complex process, and we understand with the time you have, you're not going to be able to complete a machine learning algorithm. So we're asking you to build a catapult where you are doing the machine learning by examining the variables of the performance of this catapult. You're going to use that data to learn about it, examine these variables, and then use the catapult as your tool. Put another way, if we go back to that machine learning algorithm that we saw earlier in this presentation, here's some of the steps that you'll see along the way. You're going to build a catapult. The next step is you're going to test various input factors and collect data. The data that you collect, you're going to analyze, perhaps graphically, and you're going to develop a model. Using that model, you're going to predict how to set up your catapult so that it will hit a certain target. So if you look at that diagram, hopefully you're seeing the parallel between the catapult that you're learning about and a machine learning algorithm. Machine learning is based on the engineering design process. As you saw in the introductory engineering video you watched earlier, there is an iterative process when designing any product or solving an engineering challenge. You have to research that challenge, design for it, build it, test it, and analyze it. And each time you do that, you want to improve upon it. You want to iterate on it so that you're continuously improving the prototype that you build. This is kind of the same as the machine learning process. You can see the parallels there. Iteration is a key step in the engineering design process, and a computer with a machine learning algorithm is constantly iterating to try to improve its ability to predict the answer, the outcome. So let's learn a little bit about catapults. Catapults can be built in a number of different ways, but they all have similar parts. You need to have a good base and frame so that it's rigid and can repeat its performance. It needs to have an arm or a lever that you pull back, and it needs to be able to spring back, so it needs to have some sort of elastic spring ability in it so that it launches the projectile into the air. Some catapults have a stop so that the arm stops and the projectile goes forward. And all the while, I want you to keep in mind that you are trying to get as much potential energy out of your catapult to transfer to the kinetic energy of the projectile. So you're trying to optimize the amount of energy. So you want to build something that's strong and sturdy and where you don't lose a lot of that potential energy in your device. You want as much of it to get into your projectile to go as far as it can. The other thing I want you to keep in mind is you're trying to learn about the performance of this catapult. So when you're testing it, only change one variable at a time so that you can understand how that particular characteristic of your catapult affects the performance. Let's break that down a little more. Here you can see some of the supplies that you're going to have, and on the left is a breakdown of the engineering design steps to build your catapult. We've already kind of defined the problem. You can research different types of catapults to get inspiration about your design. You're also going to put research into learning about how to optimize your unique catapult design. You're going to build it and then test it, and then you're going to try to enhance it as best you can. But all the while, when you're testing it, you will be collecting data to learn about it. Let me show you what that might look like. Here's some things you could potentially vary in the design of your prototype. You may decide to vary the type of rubber band you use to change the elasticity or the spring of your catapult. Or you may decide to change the location of the fulcrum, the point at which you bend back the catapult arm. So on the left, you can see a picture. Prototype 1 is one that varies the fulcrum. You can see there's a stack of popsicle sticks, and you can move that up and down the base of the catapult to try to change the amount you can kind of stretch the catapult arm back. On the right is a different type of prototype where you can pull back the arm of the catapult different amounts and then see how far the ball goes, the projectile goes each time. So what does collecting your data look like? Here's an example data table. In this case, we've got a column for the height, a column for the angle that the arm is pulled back, and then a measurement of the distance the projectile travels. If I show you a completed version of this data table, you can see that the height is never changed. Again, we're trying to only change one design aspect at a time. And in this case, we've varied the amount we pull back the arm in order to see how far the projectile travels. And it's okay if you don't have a way to measure the amount of degrees you've pulled it back. You can also use words like a third of the way back, a quarter of the way back, etc., or an inch of the way back, 2 inches of the way back. You can provide your data as long as you can then repeat it on your catapult when you do future testing. Here's another example where the fulcrum is moved. And so in the picture on the top, you can see the popsicle sticks are located kind of closer to the projectile end of the device. And then in the bottom picture, you can see that the fulcrum is located all the way into the very, as far away from the projectile as possible. So that's going to allow you to have as much spring as possible when you launch your projectile. And when that data is collected, you can see that this model has used the same number of sticks and has varied where those sticks are located on the arm, on the base of the catapult to change the fulcrum. And then the distance that the projectile went was measured. Let me show you how this projectile worked by showing you this quick video demonstration. So once you've gathered that data, how do you analyze it? How do you create a model that you can then use to predict the distance a projectile will fly based on certain settings? One way is to plot the data. And so here's a graph with the data we just saw in the previous slide plotted. You can see it's got the catapult setting, and then it's got the distance the projectile traveled. What catapult setting should you use to fly 200 centimeters? Well, if you look at the graph and you go over to a distance of 200 centimeters, you can see that you should get close to that setting if you place your popsicle sticks, if you put it in a catapult setting between 4 and 5 centimeters. Now, you can do things where you change multiple factors. How would you analyze that data when you're looking at multiple performance characteristics? So let's look at this. Take a look at this data. Here you can see that initially 4 sticks were used, and then the distance on the arm, on the base of the catapult was varied to get certain measurements. And then you can see the number of sticks was reduced to 3 and then 2. So all that data was collected, and then the way it would look graphically is to plot each set of data as a separate curve. So then you can get an idea of how it would perform under each of these circumstances. For those of you who like to use Google Sheets or Excel, you could plot your data in an Excel spreadsheet or a Google Sheets spreadsheet and do a similar kind of model. So in both cases, we're creating a graphical model to analyze the performance of the catapult. If you happen to get linear data, guess what you could do? You could run a regression and you could try to get an equation of that line. Here you can see that the equation of the line in this example is 0.417x plus 19.8. I'm looking at the equation up at the top part of the graph. That way you could put in any value for the pullback angle and predict the distance it would go. Any value x to predict the distance y. So here's a regression analysis that's used to do something similar to what we saw before. So that's our challenge. Let's go back and just summarize. You are kind of machine learning using a catapult. How is the catapult an example of machine learning? Well, just like a computer needs copious amounts of input data to produce a very good output prediction, you will be trying to collect a lot of data, perhaps the pullback angle, perhaps the distance along the arm, the base of your catapult, to produce a desired output, which is hitting a target a certain distance away. You're going to create a model for your catapult by graphically analyzing your data. And then you're going to extrapolate information from your graph to try to predict the distance your projectile would travel based on a certain input criteria. So that's it. That's the challenge for today, and that's an introduction to machine learning. If you would like to learn more about what types of engineers study machine learning, or even learn more about it, some topics you might be interested in researching further are AI, artificial intelligence, computer algorithms like neural networks, And also looking at the tools that we analyze the data with and that computers use as well, statistics and regression. The types of engineers that would be involved in this kind of study are really all of them, but I've got listed a few: mechanical engineers, a computer scientist, a mechatronics might be involved in combining the movement of a machine with the algorithm, with the computer coding. And then there's also, if you're specifically interested in machine learning, you might want to look into computer science, computer engineering, or system engineering. So I really hope you have fun with this challenge. Enjoy building those catapults. I hope that you build a machine that can really land on an accurate point based on your input criteria. And I hope you have a ton of fun with this challenge. Thank you.